Hey advanced geometry students, it's Mr. Donaldson, and I'm here with you today to talk about deductive reasoning. All right, a little bit different than inductive reasoning we were talking about last time, and this is section 2.4 in our notes. Let's get started. We're going to start with a real world example here today, all right? Any of you ever had a poison ivy rash? Because I can attest to you that I have. When I was a kid, man, I used to get really bad rashes from poison ivy while I was playing in the woods behind my house. You know, I'd go out and I'd get some poison ivy after playing in this one area. And then, I'd go out again, get poison ivy after playing in this one area. And I observed a pattern that when I was playing in that certain area of the woods, man, I would get this bad rash. So I used inductive reasoning based on that pattern to conjecture, you know what, if I play in that area, I'm going to get that rash again. So I stopped playing in that area. That is inductive reasoning at work. I had some data that I was observing. I saw that there was a pattern, and I made a conjecture based on that pattern. While the inductive reasoning taught me to stay away from that poison ivy, it most certainly didn't teach me why it gave me such a bad rash. To understand that, I would use deductive reasoning and talk about why. So what is deductive reasoning? Deductive reasoning is the process of showing that certain statements follow logically from agreed upon assumptions and proven facts. So essentially, you're just using facts and agreed upon statements to create some sort of logical argument. Okay? You use deductive reasoning in an orderly way to convince yourself or someone else that your conclusion is valid. Like a lawyer, great example. They use deductive reasoning all the time to try to convince juries that the evidence they presented proves their case. All right? They couldn't use inductive reasoning to prove their case. Right? Suppose they're trying to prove that let's say they're trying to prove Mr. Donaldson stole the sandwich. And the lawyer says, well, he has stolen 5 sandwiches before, so he must be guilty. But you guys can all agree that just because I stole 5 sandwiches before does not necessarily guarantee I stole that sandwich again. So they can't use inductive reasoning. No court would hold up, hey, there's a pattern of behavior, so you must have done it. You'd have to prove it deductively in order to hold them accountable for it. Let's talk more about that poison ivy situation. So there's 2 people. There's me, Mr. Donaldson, and there's a scientist. All right? Now, both of us could tell a person to stay away from poison ivy. Now, I would do it because I used inductive reasoning to decide that poison ivy was bad. Perhaps there's some scientist who's never even touched poison ivy, never had a rash, but they know that poison ivy is bad. And why did they know it? Because they had studied it, and they used facts and agreed upon statements and determined that the way the oils on poison ivy interact with the human skin will cause a rash. So me, I knew it would cause a rash based on patterns I observed. The scientists knew it would cause a rash based on facts that they knew about the oils on the poison ivy and how it interacts with your skin. So that's the difference between those 2 forms of reasoning. So how does this relate to math? Man, use deductive reasoning all the time in algebra. You follow a set of agreed upon algebraic rules every time you solve an equation. Your teacher taught you, hey, you could add the same thing to both sides. You could divide the same thing for both sides. You could use the distributive property. All of those things are agreed upon statements that we all accept as true and we can use in algebra class. So, you guys, this is the setup for what's called a 2-column proof. We're not going to do a lot of proofs in our class this year because of the weird nature of this virtual stuff and how we're losing a little bit of time, but we at least want to show you kind of how it works. So, we would call this an algebraic proof, and this would be pretty easy for you to follow. Now, one new thing to you, on the left here, we're going to write our statements, kind of the process of solving the equation, and on the right, write the reasons. Why was I allowed to do that? And the first statement of any proof is given. You got to start somewhere. So this is my given equation, and we're all just agreeing that, okay, this given equation, it's true. Let's see what we can figure out if this is true. All right? So we're assuming this is true. Let's see what we can figure out. Boom. If I asked you what was next, I hope you would all say, let's distribute. And you'd get 5x plus 10 plus 7 equals 32. And all we did was we used an agreed upon rule in math, and that is called the distributive property. Distributive property we're allowed to do. You guys learned it. It works. We're allowed to do it. All right, next thing, if I ask you what to do, hopefully you'd say, hey, let's combine that 10 and 7, because your algebra teacher taught you you're allowed to combine like your terms. So that would be 5x plus 17 is equal to 32. And all we did was we followed an agreed upon rule that you're allowed to combine like terms. I'm just going to abbreviate it with an acronym if that's all right. Next, what we do next to both sides, hopefully you would say to subtract 17, and when you do that, you get 5x equals, let's see, 25. So what rule did I use? I used what's called the subtraction property of equality. And I'm sure your teacher taught you that, and you probably forgot that that's what it was called. But for sure, we all agree that we could subtract the same thing from both sides of an equation. That's a property we're allowed to use. And then the next thing, if I said, hey, what would you do next? Your teacher taught you some point in time that you're allowed to divide the same thing from both sides of an equation, and bam, we did it. X is equal to 5 because I was allowed to use the division property of equality. So, while you guys know how to solve an equation, your teacher never made you justify each step along the way. But that's how geometry and using deductive reasoning works, is you have to justify each step of the process. If you're a lawyer and you're trying to convince someone that something is true, you got to tell them what rules you're using, what cases you're using as precedent. You got to give them why all the things you know are true. You have to provide reasons for that. All right, so here's how deductive reasoning works. We start off with some true statement. Here's my true statement. All right, like this person, if you're a lawyer, this person stole the sandwich. All right, and then on top of that, or excuse me, not this person, but the sandwich was stolen. There's my true statement. All right, we all agree. Okay, yeah, it was stolen. Now let's get to the bottom of it. All right, so then, well, this person was in this place at this time. Fact. And this person hates sandwiches. Fact. And this person, blah, blah, blah. Fact. Bam, we got this conclusion at the end. It was Mr. Donaldson. And we got to that conclusion not based on any patterns we observed, but based on agreed upon statements and facts. So here's how it works. If your initial statement is true and you give a logical argument using facts and agreed upon statements, then the conclusion must be true. Mr. Donaldson had to have stolen the sandwich. Logically, it follows from my argument. All right, so let's talk about how you can trick someone with deductive reasoning. Now, let's go back and look at this. If I were to slip in a lie right here, something that wasn't true, and I convinced you it was, then this conclusion wouldn't have to be true anymore, because then it's not following the rules of deductive reasoning. You got to build your argument on facts. Well, if you slip in, I didn't mean to write false, sorry. If you slip in something that's false, your conclusion won't necessarily be true. So let's see if you can find out where I trick you in this next one. All right, so I'm going to use that little algebraic proof thing, and I'm going to try to prove to you that 1 is in fact equal to 2. Here we go. So we're going to start off and we're going to agree that we have two variables, A and B, and they're equal to each other. Totally, that's allowed. You could have two variables that equal each other, of course. The next thing I'm going to do is I'm going to multiply the same thing by both sides of this equation. I'm going to multiply both sides by A. That'll give me A squared is equal to AB. Just multiplied. So I use the multiplication property of equality. You totally can multiply the same thing in an equation by both sides. Next, let's subtract the same thing from both sides of an equation. Let's subtract b squared from both sides of this equation. All right, that's called the subtraction property of equality. I'm allowed to subtract the same thing from both sides of an equation. Next, you learned in algebra you're allowed to factor. This is a difference of squares. We just talked about this last week. All right, a plus ba minus b. We factor the left side. And on the right side, there's a greatest common factor of b. I'm going to factor out that b. And what's left would be a minus b. So all I did was factor. All right, next thing I'm going to do is I'm going to divide the same thing. Check this out, you guys. On both sides of my equation, I've got a factor of a minus b. Well, if I have common factors on both sides of an equation, I could divide by it. In fact, let me show my work. I'm going to divide both sides by a minus b. And when I do that, what's left, notice how these, you guys probably say, oh, they cancel, and they cancel. You're left with a plus b is equal to b. And all I did was use the division property of equality. All right, and then the next thing I'm going to do is I'm going to substitute. All right, check it out. In the very beginning, we knew that a and b were equal. So instead of this a right here, I'm going to replace it with b. Because they're equal, I can substitute. So that gives me b plus b equals b. All I did was use the substitution property. And then the last thing or two things I'm going to do, I guess, is next I'm going to combine my like terms. B plus b is 2b equals b. I just combine like terms again. Combine like terms. And then the last thing I'm going to do is I'm going to divide both sides of my equation by b. And watch what happens when I do that. I get, oops, step 8, that 2 equals 1. Oh my goodness, how is that even possible? All I did was divide. Look, you guys, I used properties of math the whole way down. All right? But I had to have tricked you somewhere because we all know 2 is not equal to 1. Because if it was, I'd be endlessly rich. Because every dollar bill I had, I would take and get $2 for it. So I want you guys to think about where could I have tricked you? And we could talk about that in class. But there's somewhere in there that I tricked you. All right. So the next little part of deductive reasoning is kind of making sense of statements. So check it out. This is called a conditional statement. A conditional statement is an if-then statement. If I was born in Boulder, Colorado, then I'm a U.S. citizen. You guys, this is true based on our rules of our government. If you're born in the United States, you're guaranteed citizenship. This is a true statement. Now, this first part of the statement right here, the if part, not including the if, but after the if, this is what's called the hypothesis of a statement. It's the condition that needs to be met. The second part of that statement right here, the then part, is called the conclusion. All right, so the conclusion is the then part, the hypothesis is the if part. The converse of a statement is when you take the hypothesis and the conclusion and you switch them. So instead of saying, if I was born in Boulder, Colorado, then I'm a U.S. citizen, if you swap those, you would get, if I'm a U.S. citizen, then I was born in Boulder, Colorado. Is that true or false? Man, that is a totally false statement. I know a lot of people that are citizens and weren't born in Boulder. In fact, I am a U.S. citizen, but I was not born in Boulder. So that is a false statement. So conditional statement and then a converse is when you switch the hypothesis with the conclusion. And the point to make here is that if a statement is true, its converse does not have to be true. A biconditional statement is a statement in which both the conditional and its converse are both true. So here's an example. If today is Friday, then tomorrow is Saturday. That is a true statement. Now the converse of that statement, if I switch these, will be if tomorrow is Saturday, then today is Friday. And you guys, that is a true statement as well. If you know tomorrow is Saturday, sorry about my terrible handwriting, then today has to be Friday. So this is an example when a statement and its converse are both true. And if that is the case, you can write that as one statement called a biconditional, and it's powerful in logic and deductive reasoning because it means that statement works in both directions. So you would say, today is Friday, if and only if tomorrow is Saturday. If you read if and only if, that means the statement goes in both directions. A postulate is an agreed upon statement that we accept as true. And a theorem is a statement that we prove to be true. All right, we're almost done. Let's just talk about a couple postulates real quick, okay? So, there's a couple basic postulates in geometry. There is the segment addition postulate. It says if B is between A and C. And you guys, in math, between means something very important. It means collinear and somewhere on that line that is formed by the endpoints there. So if B is between A and C, it's somewhere on this segment that connects A with C. So if B is between A and C, then AB plus BC equals AC. You guys, totally, we can all agree that that's true. Because if this was 5 and this was 3, you would all agree that AC is 8. So that is an example of a postulate because it's so obvious we can agree, yes, that's true. The angle addition postulate, and I'm going to probably run out of time, works the same way. So let me just do this quickly. All right. So if I have some angle ABC, and D is some point in the interior of it, then the measure of angle ABD, this little angle, plus the measure of angle DBC, this angle, has to equal the whole angle. That should make sense. If this is 20 degrees and this is 70 degrees, then the whole big angle would be 90 degrees. This is obvious. We can agree upon it, and I'm out of time. Good luck on the homework.